Ladies and gentlemen, hello. This is Hossein Hashemi and Dubre Utra. So it's my pleasure to speak for Russian colleagues. And of course, I have some experiences with Russian colleagues, and it's my pleasure to now have this opportunity to talk in the GeoModel 2023. And I'm here with this talk on artificial intelligence applications in GNG, in geosciences and geology and geophysics, with emphasis on geomechanics. That is a bit new topics in our field. And also at the end, I'm going to speak a bit about how we can construct mechanical Earth model or MEM using these techniques. So my name is Hossein Hashemi, and this session is sponsored by Petrotrace Services Company, and I'm from Data Science and Geosciences Laboratory, and I'm the director of this laboratory in the University of Tehran. I'm associate professor in Institute of Geophysics, University of Tehran. So a brief introduction about myself. This is the website of our laboratory, and you see here we are putting some publications, services, and some products that is somehow written in the academia with our PhD students and also some researchers. So you can take a look after this talk to this website, and feel free, please, to send me emails for any questions and technical inquiry. So I start my talk about the paradigms of scientific discovery. The idea is that days and days will be passed, and the scientists try to understand the science in new ways. At the beginning, empirical sciences was dominant. So the human beings see something, experience something, and then the rules will come out. For example, thousands of years ago, you see this cartoon at the right, that's Archimedes of Syracuse, so 250 years BC. You see that he just go to the bath and he understand that the water rushed out, and then there are some kind of understanding, first from empirical thing, and the rules of physics will be shaped based on this empirical thing. So at that time, at those years, the paradigm of scientific discovery was highly relied on empirical sciences. Little by little, the mathematical concepts developed. And in the time of Isaac Newton, when he sees something that is empirically seen, firstly, like dropping an apple on his head, he can formulate it with the mathematics in this very beautiful and very, very known second law of Newton. And it's a kind of physical rule, essential physical rule, and known for all of us. So theoretical sciences at this time becomes dominant, and theoretical sciences started to shape. So in the universities everywhere, we start to discuss about the mathematics. Later, a bit later, at the beginning of the 20th century, at the mid-20th century, computers are developed by this man, Alan Turing, at the top, at the below right, and you see that at the top right, there is a huge computer that can normally do some tasks like a laptop that I already have, maybe, or even less than that. So you see that computers started to collaborate and incorporate with the sciences. So paradigm 3 is computers and sciences. And you see little by little also these computers develop. For example, GPUs will be introduced in parallel to CPUs. So computational sciences or computer-based sciences are shaped. In these years, we normally ask the students, and the researchers are going to put more effort on computer coding rather than developing the mathematics. Of course, developing the mathematics is still essential and will be essential. So I will have this book. I would like to introduce this book to all of the colleagues. The name of this book is The Fourth Paradigm. And in this very, very valuable book, so you can see data-intensive scientific discovery. And the book is very, very, very good for reading for all of us. And now we understand after reading this book that the time that we are now inside it is data science. So the data science is shaped because we have lots of sensory data. In geophysics, for example, we have magnetic, we have gravity, we have seismic, and we would like to put all these together. So the concepts of converting data to information or data to science, especially using high performance data, because some data are named HPD or high performance data, and the definition is that they are completely standardized and structurized in the sensory systems. So in this case, we always would like to get more data, more information from the acquired data. Okay, so I assume because there is not any feedback, I assume that you can listen to me properly and there is no any interruption. I hope it's like that. So
Yeah,
you
like
see
that.
here, okay, so it's a big data specification. I go further with this chart throughout all my slides. So it's the wheel that I keep it until the end. It shows why we name a data a big data. And I would like to show that in geophysics and in petroleum industry, we always deal with the big data issues. So the big data have one of these four or all of these four specification. And because it has all of these specification, we need some techniques named machine learning or deep learning in order to understand much from this data. Issue one is the volume. So the big data are very large. The volume of data is important and substantial, for example, seismic data. The second issue is variety. So there are variants of data sources and specification. For example, seismic and gravity, seismic and magnetic and everything. Veracity. Veracity is the issue that all data cannot be referenced equally. So this is the idea. The validation criteria of these data are different. For example, well-logged data are more trustable than seismic data. But all of these are to be used to find a unified Earth model. This is the case. We need all this data in order to reach to one solution. The velocity of data. So we have, for example, some data that are acquired very fast, some data very slow, some data are online, some data are offline. For example, passive seismic data are online data that can be also monitored online. With these four specifications, we have the big data. Now I will draw an example. And this example of big data, I think and I assume that many of colleagues in this room are specialists that are known with geology and seismic facies analysis and the concept of the facies analysis. So I try to make an example of big data from the seismic facies analysis, and it's better to say facies. We have four facies types. The first facies type is sedimentary facies or lithofacies. The concept is completely and purely geological. So we have analysis aspects like physical, chemical, or biological. So based on these analysis aspects, we have some categorizing of the lithofacies. In the analysis factor, is lateral changes within sequences of the beds of the same geological age. So we keep in mind, we are going to find facies changes in one sedimentation time. And the analysis sample for lithofacies, I mean, the data will be acquired from the cores or thin sections or outcrops. There is not any seismic or well or something else in between. So this is a big data. Because of that, I put this wheel at the lower left of my slide, lower left of my slide. Well facies or petrophysical facies. So the analysis aspects for these type of facies is some content like clay or fluid, or physical properties like density or velocity or resistivity, or lithological properties. And the analysis factor is change of different log measurements. We are going to review the changes of the log measurements. Analysis samples are depths or time series, because mostly we acquire the well logs in depths domain, and you can also do time to depth conversion or depth to time conversion, and we have time series. So they are also a part of big data, and I put this yellow wheel again the below. Seismic facies. So the analysis specs for seismic facies are seismic amplitude primarily, and secondly, we have lots of seismic attributes. It's a very, very huge story if I would like to speak about the seismic attributes. We have attributes classification based on their geometry, like curvature, like the physical concepts, energy or phase, like a geometrical thing, like the concepts of absorption. So we have lots of seismic attributes. And another analysis aspects, data-driven features, like deep learning methods. These methods, they don't use attributes. They use data and they generate their own deep learning-based attributes. I will mention about this later on. Analysis factor are lateral and vertical change of parameters on seismic cube or seismic line. And the analysis sample or seismic cube horizon or sample or wave shape. So we can do seismic facies analysis on one horizon or one map only, or on samples without mentioning their horizons, or on the wave shapes only. For example, a wave shape around the horizon in a window like minus 10 milliseconds to, for example, 30 milliseconds. So in this case, again, we are dealing with the big data because seismic cubes are very, very big. Their volume are high. Their variety, because of the different amplitudes and attributes are used. And their velocity is also because the attributes are measured based on different mathematical formulas with different errors. They have the velocity, and the velocity of generation of attributes is also important. So this is one concept. I would like to make you through data science and geophysics step by step. And finally, reservoir facies. That is very, very important for a production engineer. Finally, a petroleum engineer would like to mention about the aspects of pore, fracture, or Vagir space, reservoir phase, reservoir static model. And the analysis factor is reservoir quality index, like if the reservoir is sealing or poor, moderate to good, or good. And the sample to be studied for this reservoir facies analysis are reservoir model cube. So we have all the things in a cube, in a grid-based cube. So you see here, as I just mentioned before, in data science paradigm, we would like to reach to a unified information. That is this blue box. These yellow boxes are individual interpretations or individual calculations. based, for example, only on well or seismic or reservoir or lithofacius, then they can combine together and reach to information that is needed and necessary for reservoir engineer. So reservoir static and dynamic modeling is the goal. So as I just write this nice sentence from Canon paper, the objective of facius model is to incorporate the medium scale reservoir heterogeneity represented by the sedimentary geology into the architecture of the geocellular grid. Here again, you can see why this yellow wheel is just put. It's because we have different data with different variety and different veracity and different velocity. So in practice, there is a very nice paper in the leading edge journal in 2009 that is written by people and researchers in Stanford University. And Lisa Streit is the first author. I just would like to somehow suggest to the people to read this paper. This paper shows how we can collaborate and how we can come along with the concept of different scales in the facius analysis. At the left, we have trace, seismic traces, higher resolution than their attributes. Here we have, I hope you can see my mouse. Is it possible to have a feedback from you, Igor? You see my mouse?
Yes, Hossein, we can see a mouse. You can actually switch to the laser pointer just by
but
right click on it, because you have the white background. Yes.
Yeah. You want
a pointer options.
I just
laser pointer.
Laser options. Yeah. Okay, it's much better. Thank you for your comment. So we have a trace, seismic trace like that, and this seismic trace has much higher resolution than the seismic attributes. The seismic attributes are mostly calculated in the windows. So you can see the windowed characteristics of these seismic attributes. So you can see the resolution of XY and in depths of the seismic data and attributes when they are put together. It's about 12 to 25 meter and 10 meter. Here in the middle, we have wireline lag and core data. We have, for example, here gamma ray, and it has much higher resolution than the seismic. So the depth resolution is 15 centimeters. That is much higher. And we have facius inside the log. And the task of this paper is that you can see the color coding of the facius. For example, this dark gray is shaly sandstone. This light gray is the shale. These yellow ones are sandstones. And the task is somehow find a relationship between these facias and these attributes. This is the main task of this paper. On the other hand, finally, a reservoir geophysicist asked us a model grid that is like that. So the model XY is 12 to 25 meters. So it's like seismic. But for the Z, it is about 1 meter. So 1/10 of the seismic. We are going to the subseismic. And it is a very, very, very huge challenge. Mathematically, when you want to downscale or upscale, you shall really think about the ways of going that and the scale relationship. So you see here, there are some scale relationships and there are some facius proportions. That is the main also idea in this paper. And in the top of reservoir or base of the reservoir, finally you shall reach to the model from these data. So again, this is a data science task. Continuing this paper, he is going to go to the concept of facies proportion. So he says that, for example, in this interval, that is interval 1, you see that there is a diagram, a pie diagram, regarding these dark gray and light grays. So the proportions of facies proportion is that mostly they are dark gray, and for example 1, 2, 3, 4 are light gray, 1, 2, 3, 4, 5 are dark gray. Here again you have another concept in this part, and in this part. The idea is that how we can have these proportions and these attributes in one plane. So you see here there's a diagram, seismic attributes 1, seismic attribute 2. It can be everything. For example, phase, instantaneous phase, or windowed energy, windowed frequency, everything. So you can have these things, and with this color coding, you can see higher values or lower values of each attributes. They can be also normalized. So you see that here, for example, 1 is put here, and this means the very, very low values of attribute 1 and higher values of attribute 2. So low values of attribute 1 and higher values of attribute 2. It would be like here, and then it put this facies proportion here. The same things will go for 2, 3, and 4, and the task is to find and to predict the new facies and try to just have these cross plots and try to distinguish between these facies. In this case, you have find a relationship between attributes 1 and attribute 2 and the well facies. So it's a very, very, very careful and nice way of upscaling. That I really like it, because upscaling is very important in our studies. So I just go out of this example now and try to speak about the machine learning and the related concepts. I assume that the question will come at the end of this lecture, so I don't ask you to, but if it should be something else, just you can tell me, but I assume that it would be at the end. So you see here a chart of machine learning and the related concepts. You can see how they are collaborate together. The science, the engineering part of databases or data mining, and KDD or machine learning and pattern recognition, statistics, neurocomputing, artificial intelligence, they are closely related to each other, and there are lots of overlap. So they are completely related to each other. I can say the most important part is statistics. All these things are basically comes from statistics. And then a statistical pattern recognition are shaped. And with these Bayes rules and these theory things that I mentioned, the bit theory in my talk, but really bit, with these two, machine learnings are shaped, and then machine learning also are part of artificial intelligence. So the people from statistics and the people from computer science, mostly they would like to collaborate, and because of this collaboration, new areas of science are shaped here. And there is another diagram that shows artificial intelligence is the bigger thing, soft computing, that is my concept and my also specialization, fuzzy logic, I will mention about what it is, and machine learning, and then deep learning, a very fine thing inside. So I even also can say that machine learning is a part of data statistics. So we start from pattern recognition system. We have a real world here. We have a sensor installed here. The sensor will sense and detect a property, and then it will be recorded. We have the data. We do pre-processing and enhancement. This can be, for example, removing the noise from the data, removing outliers, normalizations, and scaling, and doing some feature reduction. And also there are some feature extraction for some algorithm, and then classification. So features are a special kind of specifications in the columns in a pattern recognition experience. In the pattern recognition experience, we have a matrix. This matrix has rows that are objects and columns that are features. So normally we need to generate enough features and informative features and distinctive features mostly. They should be make some kind of distinction. So what does a pattern recognition system look like? So we have the real data, we have sensor, we have pre-processing. It's another way of maybe more modern or complex way of the previous slide. We have feature extraction, and we can go for classification. In this case, we have some labeled data. This means we have some data that we are sure about their class, their specification. Here we have clustering that is completely unsupervised, and we don't have any teacher or any labels. Maybe we have labels, but we don't use them in the process of the clustering. We just use it for cross-check. And we have regression algorithm that, for example, in inversion, that we would like to find a model, or when we are going to have a model and we would like to predict a model for some specific data and relate them together. So in regression, we have predicted values as the output. Output of clustering are clusters assignments, and output of a classification are class assignments. We have feedback and adaptation, and we have several ways in order to improve these boxes. So this is a pattern recognition system. As I just mentioned, we have three types of algorithm for learning problems. Supervised, when you have teacher and labels. Unsupervised, when you just let the computer, in order to understand the inherent and the natural ways of distinction between objects and find these intrinsic and natural rules between data. In this case, clustering is going to find these grouping, this natural grouping, without any teacher. So this is unsupervised. We also have semi-supervised methods that are more modern ways. We have some very, very specific labels. For example, we have wells in 2, 3, 5 locations of a cube. And we have huge amount of seismic data. So we have very, very specific labels. There are algorithms that help us to propagate labels in order to have much more labels. This is semi-supervised method. And this one is also reinforcement learning. It's very, very nice topic. These are developed by the engineers in the Google company, and they just would like to do something in a way to learn by examples. I will mention this later on. So supervised learning. We have some labels that are facies code, for example, in the facies analysis. This is limestone, this is sandstone, this is, for example, claystone, everything. Or for example, this is a ceiling reservoir, this is a moderate reservoir, this is a poor reservoir. It can be everything, these labels. And we have some data that are labeled, that are our teachers. We have a machine, like it can be neural network, like everything inside this machine. Zoos of classifiers, lots of classifiers. So with this data, these labels and codes, we will have now a trained machine learning model. We have some test data. These test data are not used in this process, and they are used for validation. And with this test data, we do validate this model, and then finally, we just go for the predictions. Is it okay?
Hossein, are you asking us?
Yes. Yeah.
Okay.
Just I would like to check sometimes
okay.
the connection.
Let's find out if somebody have any questions.
Yeah, that would be very nice.
If
I just have feedback from the audience, it's much better.
Okay. So yes, I'm in the audience now. Nobody is raising the hand. What about the online?
Okay.
Alex?
So
Are there any questions? Okay, I'm now talking to the online participants. If you do have any questions to what Hossein have said so far, please type them into the chat box. I think, yes, we get a little feedback. Everything is fine, no questions. Okay, but anyways, if you have any questions, please type into the chat box. You can do that either in Russian or in English. Never mind, we'll help Mr. Hashemi with the translation. And if there are no questions so far, then we can move on.
Okay.
No questions. Okay, then let's move on.
Okay. Thank you very much, Igor. So unsupervised learning.
Hossein is offline. Hossein, you've been online for the last 20 seconds. Could you please start it over? Hossein, are you with us? We can see your screen, but we can't hear you. Go on air, yes.
Thing happened maybe. So
Okay.
now we can hear me well.
Yes, now we can hear and see you.
Okay.
Again.
Okay, so I would like to tell that for unsupervised, we don't have any labels, or if we have labels, we don't use them. So the data are mentioned as unlabeled data. We have a machine, and the result is distinction between these results. So these are two engineers that for the Google DeepMind project in 2016, they find a new learning algorithm named reinforcement learning. So there are some agents, like for example, food for a cat. If the cat do something right, then the food is its prize. If he doesn't do something good, there is not any prize. So with these actions and rewards and actions and reward system, you will somehow train the animals like cat. These reinforcement learning algorithm is like that. So you will give some input, and you evaluate the output. Or based on the evaluated output, you will give an input. So these kind of cycles will do the reinforcement learning algorithm. So we have semi-supervised learning also that I mentioned. We have very small amount of the label data, for example, in the well data, and we would like to generate the labels. In this cartoon, you see we have a small amount of label data set, large amount of unlabeled data set, like a huge cube, and we have machine learning. So we have pseudo labels. So these pseudo labels are generated based on some ideas and technologies, and then the ML model on label plus pseudo labels is semi-supervised. So this strategy is really, this time, is on the verge of the trends. So it's a kind of trend right now. So we have machine learning, supervised, unsupervised reinforcement. And here I mentioned that the applications, supervised is not used for clustering, unsupervised is clustering only. So supervised for classification and regression, unsupervised for clustering, and reinforcement learning for model-based or model-free. As you see here, support vector machines, discriminant analysis, naive Bayes, and nearest neighborhood, they are classification. And the regression are linear regression, GLM, and support vector that I will discuss about these the theories later on. Ensemble methods, decision trees or neural network are also can be used for regression, can also be used for classification. Clustering algorithms mainly are Cummings or Comedoids or fuzzy C-means or hierarchical clustering or neural network or hidden Markov chains models. So also reinforcement learning are only model-based or model-free. We have lots of others also that not mentioned here. So this is a photo of my paper that is published in the CSEG Recorder in 2008. So you see here we have different attributes, and there's a cube of seismic data. We have some places here that is somehow, I can maybe zoom like that. And you see here, these red dots are the places that are suspected to be gas chimney, and these places that are blue suspected that not to be a gas chimney. So this is from F3 North Sea data. And you see here, there are two location 1 and location 2, in order to have a spatial distribution of the better labels. And these are labels. So at the left, we have some attributes that are primarily, I would like to mention, they are in the specific range, all of them. So it's a kind of preprocessing. I mean, the vertical and the horizontal axes are same in all these figures. And you see here, there are blue dots and there are red dots. So for each of these dots, the time, for example, is reported like that. The attribute seismic is reported like that. So the energy is like that. The similarity is like that. And we have two classes because we have two colors, because we have two objects, gas chimney and not gas chimney. So we have two classes classification problem. It is supervised because we have blue and red. And we also have some attributes that we form them in these cross plots to interpret these distinctions better. As you see, the main diagonal is like that. So there's a linear thing, and we expect like that. So time versus time, seismic versus time, seismic, energy versus seismic. It just shows the spread, nothing more. The up diagonal and the low diagonal are same. So one of them can be used only. And you can see here, for example, seismic is a good attribute for distinction between gas chimney and not gas chimney. Because if you are just zoom on the seismic with a very simple line like that, you can somehow distinguish between blue and red. This one is also with a very linear, simple linear one. This is a bit non-linear. This is linear. So these cross plots shows us, and it's a kind of visual inspection before starting the machine learning. It's needed. Many people just start machine learning by pushing a button, run, and it's really very dangerous because it makes some outputs that are not valid. So these PCA scatter plots or cross plots of selected 5 important attributes are used in my lecture. So as I mentioned, there are 2 classes: chimney, red points, and non-chimney, blue points. And you can find the most appropriate attributes by just visual inspection before starting the task of the classification.
Okay, Hossein, I think I've got a question from the audience.
Please.
Okay. На английском будете, да? Okay, it's going to be in English, so I'm staying on the English channel.
Hossein, good morning.
Yeah, good morning.
Can you hear me?
Yeah.
Could you explain how do you get the feature space, and what is seismic, what is energy, and why random noise is a feature?
You want in right part, it is physical space I named, and at the left it is a feature space. So your question is that how we can move from this physical space to this feature space?
The question is, how do you get feature space? What's the way to get this feature space?
Okay, yeah. So it's a good question. Thank you for your question. I will answer, but if it is not enough, just let me know. So if you take a look at this physical space, each of these points are located in an inline, cross line, and time, like X, Y, Z. Okay, so these cubes can be filled with seismic data or with, for example, asymmetry, that is a kind of seismic attributes, for example, developed in OpenDetect software, because I use OpenDetect for this calculation, if you know this software well. So curvedness is another attribute, for example. We have also cube of curvedness. We have cube of random noise. That is simply, it's a kind of a statistical attributes. We use median, and we will differentiate of median of every sample, then the random noise will be generated. We also have similarity. That is an attribute based on similarity of the wave shapes, and also energy, and also seismic, and also time. So these attributes are used, and these are generated in a software like OpenDetect. It can be generated in every software like Paradigm software, Stratimagic, like by coding yourself, like JSON, everything. And then these issues will result in that for every point that we have an X, Y, Z, we have a kind of attribute value as well. So we have attribute values, for example, for asymmetry. And we have I would like to speak about this, for example. We have an attribute value for asymmetry, and we also have attribute value for curvedness. We just cross-plot this curvedness versus asymmetry, and we will find this scatter plot, this one. Can I answer your question?
Not so. I don't understand what is a physical space. What does point means? What point does mean? Point is a seismic event or reflection, or what is it? Is maybe
it's a seismic sample.
Auditory can help.
Well, actually, you can. We can switch to the Russian, and Igor can help you.
Maybe.
Okay.
So these points are seismic samples. These points are seismic samples. Values of the seismic samples are each attribute. So.
Okay, Vasily, can you ask your question in Russian? Okay. Okay, Vasily says he's not deep into seismics, so he'll find out with the audience the answer to the question. Okay, we can move on.
Okay, so
are there any questions?
Okay.
Any more questions? No? Okay, then we can carry on.
Okay, so I'm also ready to answer Vasily later on after the talk. So we have binary classification. So here we are going to a bit speak about the theories from linear to nonlinear classifiers. In some cases, in some of the geological concepts, we need binary classification. For example, if an event is a fault or non-fault, chimney or non-chimney, gas chimney, I mean. This means binary issues. For example, if it is a reservoir or not reservoir. These are binary. But sometimes, like facies analysis, we are speaking with multi-label or multi-class classification and not binary classification. For example, in seismic facies, we have facies 1, 2, 3, 4, 5. So it means we have 5 classes. And we need a multi-class classification, not binary classification. Normally, most of the algorithms theoretically are based on binary classification. In this slides, I would like to show if, for example, we have a training data like that. So this is object number I, and we have X of I and Y of I. From I1 to N, if X of I is a part of a larger area of data, y of I, that is label, can be either -1 or 1, -1 or 1, -1 or 1. So these are labels, and these are the values of each attribute. And if you mention, this is written in bold because it's a vector, and it can be, for example, 1, 2, 3, 4, 5 attributes, or well log and seismic, everything. It can be 2, 3 features inside. So x of I is the vector of data, and y of I is its label. It could be in class 1 or class 2. And we would like to learn a classifier. The classifier that is linear has a shape like that. So it could be, for example, if it is larger than 0 or equal to 0, it's in the class 1. And if it is less than 0, it's in class 2. So you can see here, the correct classification is down when y of I f x of I multiplication is larger than 0. You see here it's a very, very simple binary classification problem. A classifier like that can distinguish between these two classes, or this one, or that one. So it's a real question. Which of them is true? This one, or this one, vertical one, or this one? This is the thing that I will discuss about a bit later. And this is no linear classifiers can separate these two classes completely. For example, a line like that cannot separate red and blue. Some of the reds will go to the upper part. Like that also, we have some misclassification. But if we have a classifier like that, it can distinguish the class blue and red. So this part of the feature space is blue, and that part is red. So this is nonlinear classifier. I would like to mention some of the examples that these data are said linearly separable, and this data is not linearly separable. I shall say that in many of our data, the data are non-linearly separable, and we shall use some techniques to make them linear separable for modification of our pattern recognition systems. This is a linear classifier mathematical form. There is a vector of weights, W, that is a normal to the line, and B is the bias. We also named W as a weight vector. And you can see how a linear classifier can distinguish between these two. You can see also in 3D, this line becomes a plane. So a linear classifier problem has the form like that is a hyperplane in 3D. And this hyperplane is like paper, like everything, that can distinguish between 3D space. So if you have, for example, 4 features, we have the 4th axis. If we have the 5 features, we have also 5th axis. The idea is that it's a kind of rule of thumb that if we have, for example, 3 features, we are going to the best. So one way is to reduce the features, because extra features means extra complexity, means redundant features. So we are going to reach to a minimum number of acceptable features. So for example, for a KNN classifier, we go for carry the training data. For a linear classifier, the training data is used to learn the vector weight and then discard it. Only weight is needed for classifying the new data. And the concept of perceptron, that is the starting of the neural network. So neural network starts from this perceptron. And then we have multi-layer perceptron, or MLP. So the concept of perceptron is like that. And the thing that is different in perceptron to the linear classifier is this formula. So we have some initialization of the weight. And this initialization of the weight is very important. And this is a very big drawback of the neural network. Because if you just initialize weight incorrectly, your algorithm goes to another way. I will give an example for you. If you have access to a neural network box in your computers, in one of, for example, the applications, whatever it is, in Geolog, in Vellog, or for example, in seismic facies, like open detect, like the algorithms that are made on neural network, shallow neural network or older neural network. The idea that makes a critics for them is that if you run them several times, several outputs will come out. Which of them is the answer? You don't know. So in some of the algorithms that are more stable, they use, for example, 25th run of the neural network, and then they sum up the ideas. But still, this initialization of the weight is the weak point of the perceptron and neural network algorithms. And you see here, there is algorithm for misclassification, this sign function. And I don't go through the mathematics because I know that this is not the classroom. I just would like to show you, and you can review the mathematics later on. And I would like now to come to another updating of these weights. So these weights before update and after update, you can see the border is just changed, and this change will be done until the correctly classified or a misclassification criteria is somehow down. This is a cartoon that shows how biological neuron and computational neuron are related to each other. At the left, you see biological neuron. At the right, you see the computational neuron. On the top, there is just one neuron, and at the below, you see some neurons that are networks of neurons or neural networks at the below. So if just we stick at the A and B that are on top, you see at the A, there is dendrite, cell body, axon, and terminal axon that are a neuron in my mind, in your brain, in my brain, acts like that. And they have a clue for that. And with the perceptron method, they just have X1, X2, and Xn as the data that are sensed by these sensors, X1, X2, Xn. The weight factor is W1, W2, W. This is the initial weight factor. That is, we don't know about it. We just guess it, initialized by randomness. And then in this box, we have a sigma that is somehow multiplication of this data to this weight plus this data to this weight, this data to this weight. And at this sigma, then the idea of the neural network or some neurons and perceptron is that this F function. This F function means that it doesn't give us directly a value. It shall go through a transfer function or activation function. If it reached a threshold, then there is output. If it doesn't reach to that threshold, there is not any output. So this output can be labels. The innovation of the neural network is this F function and this weight function. When there are several neurons related to each other, data from this neuron goes to this processing unit, then there is another neuron, there is another neuron. So we have input layers and we have weights, and each layer, input layer can connect to a hidden layer. At least one hidden layer is needed. It can be also 2, 3, 4, 5, but at least one hidden layer is needed. And then it goes from this to this and this to this and this to this. Everything is connected, and then you have an output layer. Of course, still it is not a fully connected neural network, but it is a shallow neural network that we normally learn about it 10, 15 years ago. And I will put this yellow wheel in order to understand that all these issues are from data science. So there are good news and bad news, and the message of this slide that neural network application is very tricky. It's not a push and go process. You see a software and there is a run, and you just click run and you expect good results. It's not a good results. It's cheating. It's very, very important that somebody judge these results, and there's a enough constraint behind this algorithm, artificial intelligence algorithm. Otherwise, these neural network things are misleading. So the bad news about this neural network is that the choice of target is variant. The number of hidden layers shall be found out. 1, 2, 3. How many hidden layers is enough? number of units in each hidden layer, how many neurons in each hidden layer. The type of activation function is very important. It should be like sigmoid, like a step function, whatever. The initialization of the weight that I tell you is very, very tricky. Which training algorithm, like least square, like gradient descent, steepest descent, which of these training algorithms is good? The learning rate, that are steps of the learning, is very important. Very, very fine learning steps has some problems. Large one has some another problems. The conversions, when it will be stopped. I mean, the learning process is going to be stopped. And training epoch or time is also bad news. This means we have lots of parameter tuning for neural network. These are bad news. Good news is that people work in their paper. For example, they mentioned that only one hidden layer can approximate any arbitrary continuous function. This is understood by Chebenko in his paper. So a neural network with one hidden layer is enough. It's not good to go for two hidden layers or three hidden layers when your problem is continuous. For a problem with more than two class, that is like facial analysis, two hidden layers is suggested by Lippmann. So this is a hint for us. Neural network with one hidden layer can give a good approximation for any continuous function. This is also mentioned by Hornig in 1993 in its paper. So, but there is a very, very huge problem also for neural network. If you also have all these parameters tuned very well, still there's a problem because the answer of the neural network is not unique. What is the best W, for example? This border is good, this border is good, this border is good. For example, between 1, 2, 3, 4, these three, you see that all of them has zero misclassification error. But in reality, which of them is correct? Neural network has not any idea. It says that only run the algorithm for several times and then somehow get a kind of voting between the outputs. Not satisfactory for a scientist. Here, a very, very nice Russian, I would like to mention and to emphasize, a Russian scientist. And he is going to, Vapnik, is going to invent a new concept named support vector machine. So this support vector machine is a Russian-made classifier. So it's much more understandable and better than these neural networks. And some people use neural network and support vector machine together. And I really like it because instead of relying on all data, it relies on only selected data. That these data are named marginal data, that you see these with some kind of circles around. So these data, these blue and red data that are inside this border are named support vector. The idea is that among all of these black lines, the one is correct that can make a larger margin. So the larger distinction. So for example, this dark one can, but if you just leave it and use another border, I can in this case exit and use a tool here in my PowerPoint. So why this red line is not the solution, for example, and the black one is the solution? Because if you would like to make some kind of parallel And I will use some graphics in order to show you what I mean. So if I just generate two parallel dashed line from this red one, you see this one is a strict somehow reach to this support vector and stopped. So it has a very, very narrow border. So the width of this border is like that, and the width of this border is like that. So simply, this is not the solution. And the support vector machine dropped this one and just says this black one is more convenient because it has the border with the higher widths, or we can say larger margin. So it's a maximized margin. Vector machine is a maximized margin machine that is invented by Russian and scientists, and this is really a kind of innovation to neural networks. After 10 years of starting neural network, support vector machines are discussed, and some people, in order to use all the properties of neural network and support vector machine, they go to combine these in SVC neural network. And you see here, when we have nonlinear data sets, nonlinear space, we have a kernel tree. With this kernel tree, we go from this nonlinear to this linear, and then we draw the support vector machine. And so support vector machine originally is a linear classifier, but it can go for a nonlinear also distinction with this kernel tree. So kernel tree also makes it nonlinear or appropriate for nonlinear problems. And I really like it. For multi-class classification like facies, it can also be used. So it's a multi-class classifier. It can be also, primarily it is binary, but it can be also used for several classes. So one class, one versus one, OVO, like that. For example, A versus all, or B versus C. This is OVAB, one versus all binary. And you see this space has not any class. So it's not in class, it's not in class A, B, or C. The points that are put in this feature space in this area, they have not any class. This is one bad thing about this method. But this method is one versus all continuous, and you see it's like, for example, a Mercedes-Benz arm, and you see every points in this space are somehow related to class A or B or C. The concept of soft computing, or computing with words. So you see here, it goes from east to west also, because the people of east, they have some interpretation in their speech, normal speech. So Professor Latifzadeh is half Iranian, half from Azerbaijan, and he's died some years ago, and he has a laboratory in American universities, MIT, and then the institute, his institute was Zadeh Institute, and he says that one way of solving the mathematical problems, especially for sciences like geophysics and GNG, because we have interpretation. You know what we have as a difference with physics, for example, and chemistry and other sciences. They don't normally go to interpretation, but we rely on interpretation. So my interpretation is something like that. Your interpretation is something like that. So it says that how we can compute with the words. For example, you say this interpretation is good enough. Stop it. How we can formulate it. And this is done by fuzzy logic. Another concept that they mentioned is about precision and significance. So he wants to say, look at these two cartoons. A man stands here, would like to warn this one that a weight will drop to your head. he can say sentence like that. Let's take a look at this. He can say that a 1,500 kilogram mass is approaching your head at 45.3 meters per second. He used the precision. This one says, look out, only look out. He doesn't says about the weight, about the mass, everything. He said, look out. He just emphasized on the significance. So I ask you, and I ask Igor to ask you, and just give me an answer of the people in the salon, in the maybe in the online. For geophysical, for G&G problems, for reservoir problems, which of these are mostly important, precision or significance? And what are the reasons of the people and audience? I ask you as a question.
Colleagues, anyone?
Vasily Ryzhov, I think precision, because we have know how many oil, we don't need arrogantly.
Okay, one more answer.
Alexander Volkova, Tomsk Polytechnic University. I think it is significance because of the question of seismic resolution.
Yeah.
Okay, anyone else? Maybe someone from the online?
Okay, so both answers are, I think, are correct.
No.
Sometimes we need precision. But you know that if we are just rely on the precision and the mathematics and the percentage of the oil, all these calculations have some kind of errors. And we can say in many applications, significance is also more important because we don't have any resolution. He mentioned correctly, seismic data has the limited resolution. And we just would like to reach to a kind of interpretation that normally this interpretation is somehow qualitative rather than quantitative. So the role of significance in the science is very important, and this makes fuzzy logic to be applicable. There are some also other examples. For example, in the hall that we are inside, some people maybe says that now it's cold, some people say it's warm, some people say it's hot. So it's really related to their mood. There is not any distinct answer that now the room is cold or warm or hot. Maybe for some of us it's hot, for some of us it's warm, some of us cold. This is what is exactly happened in these issues. So with a hard clustering algorithm, we have some classes like that. Look at this. And in some soft clustering, we have class overlap. It means that this data will belong to this cluster, for example, for 80%, and belong to this cluster for 20%, and 0% to this one. This is the idea of soft clustering. It's much more relevant to the idea of the facies, because some facies are somehow related to this class, somehow related to that class, somehow they are limestone, somehow they are argillic limestone, somehow they are sandstone. So because of this inhomogeneity in the earth, we also have, for some purposes like geospatial soft computing is much more important. We mentioned to one of the papers with my PhD students in 2022 that is published in 2 journals, and it's the algorithm is in the Journal of Seismic Exploration and the main case study in the Geophysics Journal by SEG. So we use the concepts like, look at this flowchart. First of all, it is supervised. We use extended elastic impedance attributes. That is very, very informative. And we use it for fluid replacement modeling, or FRM, to find the fluid type and discrimination of fluid types. And we use fuzzy clustering and SVM. So both fuzzy and SVM is used. We do well analysis. Rock physics and FRM modeling using a well data set is done. Then there are EEI spectrum in the certain interval of the chi angles. So there is a parameter like chi angle. Each chi angle can be devoted to one fluid. And it is scanned from minus 90 to 90 angle for each saturation scenarios. There are different saturation scenarios. And the cross plot of extended elastic impedance spectrum of each saturation scenarios versus chi angles build this EEI, a template. And then we use to select the chi angles with the most different EEI for different type. Here the seismic analysis is coming. So here just only done for well. Seismic is in this way. We also do AV analysis of pre-stack, and we reach to some AV attributes like intercept and gradient, and it will be continued here. Combining these 2 information, well and seismic, we have EEI reflectivity at the desired chi angles, and we hope that these chi angles give us a cube of fluid. So we don't go for upscaling at all in this. And upscaling is not done because we just mentioned to find the kind of regression between attributes and with chi angle target and in the well. So this is a kind of ideas. So EI model-based inversion of EI reflectivity and segmentation of them using fuzzy seamings, and then we use fuzzy segmented data to train SVM, and then fluid discrimination map is generated. So we do careful things, and here you see the results. For example, this is for chi angle plus 90, and this is for chi. D map is for chi angle minus 90, and they are calculated in one data set, in one map, at the top of the reservoir with 8 milliseconds center the window. And you see that there are different answers in different chi angles, and we do use these maps in order finally to model. This is the well log, and this is the seismic, seismically based proposed method. And then you see that green is gas, red is oil, and the brine part of the reservoir is blue. So these kind of maps are informative for reservoir characterization. Okay. So I would like to say it's a fresh example of soft computing plus neural network. Another example is SOM, or self-organizing map. It's very, very nice unsupervised classifier for clustering. So it's a kind of lattice structure behind it. It's a neural network, unsupervised neural network, and there are some kind of topologies like that. The idea is to have a lattice structure over the feature space, and then the neurons are competing with together, and one neuron is the winner. And the lattice structure here is 2 by 2. So SOM is acting like that. We have a cloud of data like that. For example, attribute 1 versus attribute 2 is this blue cloud of data, and there is a lattice structure 1, 2, 3, 1, 2, 3, 4, 5 1, 2, 3, 4, 5. So 5 by 5. So this lattice structure, first of all, this neuron is the winner. It can take the attention of this data point. So it really changes the lattice, and we go that. And finally, the lattice structure shape is fitting the data. And when it fits the data, we are down, because after some iteration, SOM lattice fits the data. It means that it can model the data. So there's mathematics beside that. I don't go to the mathematics, just I use this shape. I also go for this paper in EAGE 2017 in Paris, that we have a team of researchers from France and Iran, and we have this SOM workflow, and we write the software. One thing that I do, especially in my laboratory, when we do something, we make it package. And these packages are valuable and also can be written for the industry. So we have a nearest neighborhood facies like that, and we have seismic facies using these thicknesses and this structure for different lattice of SOM. So it's a kind of semi-supervised technique, because we use well and the seismic together. The clustering with the SOM unsupervised part, but the labeling from the wells is the supervised part. So we name it as a semi-supervised method. So any question till now?
So, Hossein?
Yeah.
Yes. So, are you waiting for further questions? Colleagues, are there no questions so far?
Because I don't see the people in the audience. Maybe the webcam is off, but okay. Yeah.
Yes. I see no raised hands so far. Those who are online, if
Yeah.
you have any questions, please raise your hand. It's at the bottom right-hand corner. There's a button called Raise Hand. Or you can type in the question into the chat box. So, okay. I think there are no questions so far.
Okay. Okay. So we are now starting a new topic, and the topic is about the new way of using this AI technique. So as I told you about the history, this starts from statistics, from naive Bayes and Bayes rules. It starts from probability in statistics many years ago. It's not a new thing. I mean, artificial intelligence is just a way to say things in a modern way. A statistical pattern recognition is the basic for all these things. Then neural networks are a kind of simulation that is done by the task, and especially with the things and papers of the Rosenblatt. These perceptrons are made. Russian colleagues, Vapnik, they are going to this support vector machine. Some other colleagues use fuzzy logic, soft computing, and the machine learning is going further. And recently, I mean, in the last 5-7 years, you see many papers of deep learning comes to our society. So these deep learnings are somehow a kind of image processing, and the idea of deep learning, I like the idea, but it's not maybe the best answer all the time. Here, I just would like to mention one of these noun structures of deep neural network or deep learning that is named convolutional neural network, or CNN. We have an input layer. We don't have any attributes. Every features will be made from this image. So this is one difference with a statistical method and with shallow neural networks or support vector machine or whatever that I mentioned before. We start only from seismic image. Of course, we can add seismic attributes, but normally the standard way is let the deep learning algorithm itself makes features out of this image. So by some kind of mathematical thing, they will find some features, like by rotation, by cropping and rotation, and these things, these issues. Then, after finding some features for this image, there's a convolution layer. So it acts like a filter. So a small part of the image is just selected, and there is a convolutional filter for that. There's a pooling layer, convolutional layer, pooling layer, and fully connected layer. So the layers acts like that. One convolutional layer, one pooling, and one fully connected is needed. It can be also some other convolutional layers. Then you reach to, for example, an idea that is false or not. So three kinds of layer for CNN, for convolutional neural network is needed. Convolution layer that do convolution, pooling layer that do some kind of pooling and selecting, and fully connected layer that somehow makes all these information to one answer or one label. So for neural network or deep neural network, for sure, it needs lots of mathematics. So I omitted for this conference because I would like finally reach to these geomechanical concepts. So more hidden layers is needed than the ordinary shallow neural network. It's a bad thing. There's no control on these. But it's like, for example, many things that becomes brands in the publications. So more activation function are needed. Fitting to more complex models is of course possible because of these activation function and more hidden layers. You can fit to more complex models. It has instability problem, and it has high number of variable problems. It has convergence problem, it has exploding, vanishing gradient, it has overfitting problem, and high computational cost. Some of these issues are resolved. For example, by using Adam optimizer, this convergence problem is a bit better. But actually, still deep learning has some critics among the people who comes from statistics especially, and they don't trust it so much. But it is a kind of, as it said, image processing. They take a look at this seismic data and all these data as an image. So you see here a convolutional layer. There is the input image like that. And this is a filter, -101. This filter is an edge finding filter. And you can convolve this filter to this image from this part, and then go further to the convolution. Like that, like that, like that. And then you finally have feature maps like that. With this filter, you find these, and with this filter, you find this one. As you see here, it is a kind of vertical edge detector because the filter operates like with these multiple values of the filter. You understand it's a vertical edge finder. This is a horizontal edge finder. And if you mix these two, we have edge image. So this is edge of this picture. So as I told you, CNN is a much more image processing technique. We have filter, we have input image, we have pixel of neighborhoods at the main pixel. And for each of these, we have a convolution. And then some of our products, its output image is like input image, I mean, in the case of size, and you have an output like that. So this is how these techniques are used. In the pooling layer, you have some average of pooling. So you have this kind of CNN, and you can pool like averaging maximum or minimum operations. For example, between these 6, 3, 8, 10, average pooling is averaging simply. So 6.75. Maximum pooling is 10, and minimum pooling is 3. So if you have something like that in the as the output of the convolutional layer, the answer with maximum pooling is here. For this box is 7, for this box is 29, for this box is 31, for this box is 21. So there are also different things, why you use average pooling, why you use maximum pooling, when you use average pooling, when you use maximum pooling. So these adjustments are very tricky. And still, I would like to say that it's not good if a company starts an R&D without mentioning to these specific things. So after this pulling, there is a fully connected layer. It is flattening to like that. This one is flattened to this one is flattened to this one, and this one is flattened to this one. And this fully connected with some weights. That is also, again, initialization is an important thing. You have blue or red as the final class. So this is the way that deep learning CNN works. For as I said, for every CNN you need a convolutional layer, pooling layer, a fully connected layer at least. These are feature extraction. As I said, in deep learning you don't need seismic attributes or other attributes or well attributes. Only you start from one well log. Only you start from one seismic image, and then you have output. So there are challenges like overfitting, like exploding or vanishing gradient, slow convergence, and computational burden. And the description of, for example, overfitting means that the loss function is low for training data, while we have a high value of the test data. And the solution is we can use bigger data set, we can use validation and test data set, we can use regularization issues, and we can drop out some data. Exploding vanishing gradient description is a successive multiplication of gradient in the directive of the activation that is repeated with backpropagation, and we can go for batch normalization, we can go for activation function determination, and also clipping the gradient. A slow convergence, sometimes it needs high computer power to run a CNN. We have zigzag movement and gradient descent algorithm, even ADAM that is mentioned here, that is a moment-based gradient can be used. We can go for mini batch and batching and transfer learning. And computational burden, high number of variable data, big matrix, and GPU computing. That is, GPU is a kind of application that is inside our graphic cards. And if you have a graphic card like NVIDIA, you can find there are different types of these cards and different GPUs. So, batch normalization and dropout layer. You can see some of these examples. I don't go to the theories, but it's very, very essential. And most of the application I developed, I really take a look at these dropouts especially. And it's very important to have also batch normalization layer. To speak about these issues, and I hope that you understand till now. If there's any question, please let me know before I go further. And I think that we shall omit this CNN because the issue of CNN is discussed fully in the papers of the people from computer science, and we only need to know about the ideas. Any question till now?
Okay. Colleagues, other questions?
So we have these timelines from 1998 to 2019 from different CNN architecture, LeNet until ResNet. And all of these issues have some ideas behind it. Why, for example, when we are going to Inception V4, when we go to LeNet 5, and there should be enough reasoning system to choose one of these architectures. For example, this is a LeNet, a basic structure, older CNN, and you here see that there is a digital image by 32 by 32 plus 1 bit. It is a convolutional 3D convolutional layer, 28 by 6, a bit less size than this one. Pulling is down and it is going to the less size again, less size to convolutional layer, and next pulling 5 by 5. And then there's a fully connected, two fully connected after each other. And you have labels, estimated labels here. So we softmax. because I don't think, I don't know about the background of the audience. And I just understand that because it is geomodel, most of the people are related to this petroleum industry. But I just would like to mention that using these algorithms is very, very, very dangerous if you don't have any knowledge of their mathematics. And push and go is not a good thing. This is the message of all these slides. I don't want to teach, for example. I just would like to mention that autoencoders are some blocks like that. They have an encoder part and decoder part. This is decreasing the size. This is increasing the size. And we've reached to geomechanical. That is our application now. Any idea till now? Any questions about the generality of the machine learning? Because I don't go for machine learning anymore. It's finished. And we are starting a new topic, geomechanical. And I think geomechanics is going to be widespread in next years. Because also it's now very important. Now, you see here, somehow we can say, and it's important for us to mention about the stress and the distribution of stress in this stressed body. Earth itself is a stressed body. So we have shallow burden part, shallow overburden part, this part. For example, in the marine area, it's the seafloor subsidence. We have soft layers like this layer. Still, the rock is soft. And we have bedding, we have parallel sedimentation. And sometimes when we have a log well here, we have some kind of failure of the well in this because due to the shearing characteristics of this one or two. So for engineers, it's very important to know the drilling hazards. And geophysicists can help, or reservoir engineers can help in order to avoid borehole breakout in these shallow overburden and soft layers. And because of compressional stresses at the overburden wall. And you see here, there is a pre-existing fault. This is a reservoir seal here, and there's a reservoir rock here. So this reservoir is somehow, it's a kind of, I can say, reservoir compartments, and there's a compaction, welfare in compaction, porosity permeability reduction is happened here. There's a fault here. This stress body totally shall be mentioned. So in geomechanical modeling, they said that in order to understand, in order to reach, for example, to a facies model or to a permeability porosity, we shall also include the concepts of stress. So especially it's developed the idea because the fractured reservoir are coming to the studies. So oil is trapped in fractured porosity below a disconformity. You see here is a basement rock that is fractured and there are shale over it. So it's a stress body. Oil is trapped in the fractured porosity adjacent to fault plane. And it's very important to understand the characteristics of these fractured zones. In this case, we need to build mechanical earth modeling, or MEM. If I take a look at these two seismic maps on the data that is named Ship Shoal in 3D Seismic Cube, and you see there are two, the task is done by Western GECO and it is published by Becke in 2012. You can follow the stress arrows. There are salt they appear here and here, and these are in two different time slices. So for these different time slices, one is, for example, A is for 1 second and B is for 2 seconds. You can see that there are some kind of wells here, two wells here, well A and well B, located here and here. For example, here for well A, you can see with red and blue, the values of low and high shows how this well can be resisted with the breakout. So the issue of the breakout is very important near the self-tools, for example. In this, the message of this slide is to show you that for each of the wells, it's needed to investigate about the stress, and then this stress can be somehow go to the 3D, to the seismic stress cube, and this seismic stress cube can be one of the attributes used for facies analysis. Okay, so when you are going to deep learning, you don't have any access to these data, and it's very, very hard to go for deep learning and code it. But for support vector machine and combination of the fuzzy logic and these things, you can use this stress data in the facies analysis. So you see it's a mechanical earth model for the kind of geological point of view at the left, and the concept of mechanical earth model is geologically is shown on the left, based on local and regional geology only. No geophysical data is used here, and the detailed mechanical stratigraphy provides information about the facies type and local deformation mechanism in the middle. So this is mechanical stratigraphy log of this geological thing, and you see it's a stress state like sigma of V, sigma of H, and sigma of H correlation, and you can see this is the mechanical stratigraphy. So we also have some logs that can help us. Also, some of these logs are computational, like Young module, that is computational log, or friction angle, that is computational. So you can see these Poisson ratio, these logs, and these elastic strengths will be demonstrated by these logs. And if you see, normally we expect something like that based on only this stratigraphy. But what is exactly happened? There is a trend of P of P, and sigma of H and sigma of a large capital H is just mentioned here. So maximum horizontal stress is shown by sigma of H, and the minimum horizontal stress is shown by sigma of H. You see that also P of P is predicting pore pressure, and the sigma of V is the vertical stress. So with these lines, we understand that what is exactly seen in a reservoir is this one and not this one, based only on the mechanical stratigraphy and 1D models. This trends line shows us about, or give us an idea about the stressed body by depth. So this is the direction, for example, of sigma of H from west to east, and this is north, and you can have an azimuthal look at this mechanical earth modeling. So with this paper, that's a very nice paper, you understand that this parameter can use to predict the reservoir properties with a more exact and precise way, understanding and considering the geomechanical effect. And if you would like to summarize all things in the paper, in this paper, there's a good table. And you see here, for example, mechanical stratigraphy, this is the property, and the source logs for understanding this mechanical stratigraphy are gamma ray, density, resistivity, sonic, compressional velocity. Also cuttings and cavings and sequence stratigraphy can be used, but these are the main logs. Pore pressure by V of P log and sonic log, I mean, P velocities of P, and check shot survey and resistivity log. And there are other sources like interval velocity from seismic. It's very important. There is a software by Paradigm use this interval velocity for seismic pore pressure prediction. Vanguard. It's a very, very nice module. I like it. Formation integrity test and daily drilling reports. Overburden stress is another property that is sigma of V because of the overburden and just this cake model that is shaped. Source log are bulk density, and cutting also other sources. So for every property of geomechanical properties, there are some logs. The idea of seismic facies analysis based on geomechanics is to consider also these properties in the seismic facies. So this is a novelty, and I think it's the necessity for especially fractured reservoirs. So there are different data. I just put this yellow wheel again because there are different data: regional, drilling, geology, and geophysical. For example, for geophysics, we have seismic, check shots, and wireline logs. In geology, we have structural maps, and the ranking for geological modeling based on this paper is ranked here. And you see that, for example, seismic lines are ranked 1, structural maps and well location maps, formation tops are needed, well surveys are needed, end of well reports, and tectonic setting and regional setting. So when we have to like to combine these things together, we need AI. And the qualitative ranking indicating the value of existing data for drilling planning. Rank 1 is information of the sufficient quality and depth coverage to meet drilling planning objectives. Rank 3 indicates the significance gap exists in the type, and rank 2 is intermediate values. So some companies like Schlumberger started to think about how to involve geomechanical things inside the seismic interpretation, basic seismic interpretation. So you see here in this diagram, there is a scale changes from basin scale to the field scale. And the basin scale, we have few measured data available and large uncertainty in the model. And in the field scale, we have large amount of data available and reduce uncertainty in the model. So you see here, there should be different MEM workflows from basin model that is MEM 1D to field scale that is MEM 2D and 3D, and seismic data cooperation is needed. So in order to make a mechanical earth model in 3D, there should be use of AI in a very, very distinct way, like this entire cycle. You have seismic data processing, petrophysical, well log, and then fault interpretation, horizontal interpretation, velocity analysis, wavelet estimation, rock physics. You can use only by rock physics to 1D MEM, but from the horizon interpretation, you want to find also low frequency model and seismic inversion, lithology classification, mechanical properties, depth conversion, grading for the things. Also have lithocube and stress strain model that is the basic for the input of 1DM to this stress strain, and you have fracture system, and you have drilling plan, well trajectory, and prospect. So this fracture system that is MEM 3D is the input for this application. And still, again, this yellow wheel is informative from the beginning of my slides. So there are some kind of ways forward and future of the geomechanical MEM. So sometimes the people need to do some specific region of interest, like ROI or shape-based well seismic geomechanical facies analysis, or MEM modeling while drilling. I think it's the time for some Russian interested companies to build these softwares, and in these cases we can be helpful. Thank you for your attention. I'm looking forward for future collaboration, either in the courses for the industry in Russia and academia, of course, and also for the software development services that normally we do. And I hope that I had this opportunity to work in the Russian market since 2018. I developed a software named SizeArt that is now registered, and also the companies use this. And I hope that these collaborations are going to be continued. And again, I thanks the colleagues of GeoModel Conference, the colleagues of Petrotrace Services Company that helps me to enter this conference. And I hope we can collaborate together in order to find some ways for software development. I'm free to answer your emails technically or about administration things by hashemi@dsgeos.com at the below of this page. Thank you for your attention. And now I'm ready for the questions and answers.
Hossein, thank you for good presentation about huge history of science development. And could you explain where do you apply machine learning approach to improve geomechanical model? Actually, I didn't see that moment.
Okay. So when we have this, when we have lots of data, machine learning is needed, is a necessity. Okay. So if you take a look at this slide, you see different data with different resolutions. Seismic data. We have seismic data here, seismic processing, petrophysical, well logs. And when we would like to combine all these things together through the slides that I just presented, we have also 1D MEM here, in order to make this fracture system finally. Using all these cubes and these objects that is mentioned here and is also presented here, you need machine learning to make this nice mud weight cube, for example, or fracture cube for you, based on these mechanical earth modeling predictions. So these two cubes are made by machine learning techniques.
Could you share the technique?
Yeah, the technique is, of course, under development by me and by others. But my approach is based on fuzzy logic and support vector machine and neural networks. So we are going to find the fracture cube involving not only seismic earth, because you know, if you are aware of this software thing, there is a software named OpenDetect. They have fracture cube algorithm now. Their fracture cube algorithm they use seismic attributes. And in this model, we are going to find a fracture model that is even used geomechanical concept rather than only seismic attributes. This is the idea.
Thank you.
Thank you for the presentation. I would like to go back to the slide number 25, because you go fast on the next slide. As I remember, you said that we need not to push button and analyze our data. You see the dependencies show us dependencies between the data, but you don't speak anything about how we can analyze it. For example, I understand that asymmetry and curvedness not clusterates on the two clusters, and which my next step. I need to delete all asymmetry data, or what I need to do with this data.
Thank you very much. Thank you very much. So just I would like to make an idea about how we can use this crossplot for visual inspection. Just take a look at this part. I mean, up diagonal. We start from this. You see here, we have time in this row, and you just change it to here we have time, This differentiates between blue and red very well. So I just put one tick here. I even can use some shapes like an acceptable thing, or even this one is okay. So this one is okay because it differentiates between blue and red. This one is okay because it's differentiate between blue and red with a linear classifier even. This one is also okay. This one is okay. Still there is a differentiation. This one is also okay, and this one is also okay. So this shows that attribute time is a good attribute because with different attributes it gives kind of distinction. I keep it here. I use time. I go to the next attribute, that is seismic. Seismic versus time is also good. Seismic versus energy is so it's good. This one is not good, so I don't put this one for just use another type, and yeah, make it like red, like yellow. So this is also a good one. I pointed. This is not good, so I don't put for these. I don't put for these. I don't put for these, and I don't. That's okay. Only two. So seismic itself get two. So it's a kind of visual inspection. I shall either change my labels, because with these labels, these outputs will become, or change my attribute set. So seismic get the ranks of 2. And here again, you will get the good rank for this energy versus time, versus seismic, it's okay. Versus this one is not okay, not so okay, not so okay, just 2. So I just put 2 for energy because there are 2 distinctive borders. Maybe this one is also good. It's a bit good. So I just put 3 for energy. 1, 2, 3, 4, 5, 6 for energy. So time is the best attribute till now. Energy is the second, and seismic is the third. Do you understand how we can use these cross plots? Visual inspection now?
As I understand, we can give weight coefficients to the data.
Yeah. It's a kind of visual thing only. It's not any mathematics. It's like just checking the cross plots.
Okay, thank you.
Yeah, thank you very much. Thank you very much for the time and consideration. And I hope to be in the conference for the next year in person. Thank you.